All right, so let's do hypothesis test for a mean with one sample. Okay, so let's say you know, someone claims that the average weight of, I don't know, average weight of an egg is 100 grams. I have no idea. What's the average weight of an egg? We'll ask Google. What? Okay, so we'll go with large eggs. 2.125 ounces per egg. Okay, 60.24. All right. So someone says the average weight of an egg is 100 grams. Okay, you think that is too much. Okay, so you take a random sample. Okay, we're going to take a random sample and here's our properties of our sample. Okay, so we took 20 eggs. Our average weight was 65 grams. And our standard deviation, let's say, is 15 grams. Okay, so does our sample provide evidence that the average weight of an egg is less than 100 grams? Okay, so this is our question. Okay, let's, we'll do this one step at a time, okay? So go ahead and take a moment here and come up with the appropriate hypotheses to use, okay? So pay attention and say, you know, our question says, does our sample provide evidence that the average weight of an egg is less than 100 grams? So I'll give you guys a minute here to figure out the appropriate hypotheses to use. Okay, we're gonna do our hypotheses here, okay? So we need to create a null hypothesis and an alternative hypothesis, right? Okay. So we're dealing with means, okay? So what symbol are we gonna have in our null hypothesis? Mu, great, okay? So I'm gonna have a mu in my null and mu in my alternative. The null hypothesis always has an equal sign, okay? And so what we have is mu is equal to, and we wanna know what is do we have evidence that the average weight is less than 100? So our null would be that the mean is equal to 100, and then the alternative will be that the null mu is what? Less than 100. Okay. So we're looking at this, and we have 100 grams as that. Okay. So what is the value of mu 0? Mu 0 is equal to 100. So this number 100, this is our mu 0, which comes into play in our later formulas and stuff like that. All right, is this okay? All right. So we have, we've already labeled our data here, okay? It might be written in paragraph form, okay? So here I've written out n is this, x bar is this, and s is equal to this, okay? But it could also be written out in paragraph form, where something like, you take a sample of 20 eggs, okay? You find the average weight to be 65 grams with a standard deviation of 15 grams or something like that, okay? So that's, it might be written in shorthand, not shorthand, it might be written in paragraph sentence form, and then you would just have to pick out n is 20, x bar is 65, and s is 15, okay? And I'm hoping we're comfortable with doing something like that. Okay, so we have our hypotheses here. All right. Step 2 is our preparation. Okay, and we've already kind of done this, right? So our prep, we have mu 0. We know this is 100. We have n is equal to 20. X bar is 65, and s is 15. Okay. So we're going to do our calculations, and we're going to use alpha equal to 0.05. Okay. So our calculations. What do we have? Standard error is equal to s over the square root of n. We have t equal to x bar minus mu sub 0 over the standard error. Okay, and then we're going to get our p-value. Okay, so I'm going to go ahead and do this part for you, and then I'm going to have you guys go from the t value to your standard error. Okay, so our standard, t value to our test statistic t to our p-value. Okay, so our standard error, I'm just plugging in the numbers we have. S is 15. I'm going to divide this by the square root of what? 20. Okay, so I do 15 divided by the square root of 20. And this is 3.354. Okay, my test statistic t is going to be 65 minus 100 divided by 3.354. Okay, so in the numerator I'm going to have 65 minus 100, and I'm going to divide this by the answer that I had previously. Okay, so here I get negative 10.43. Okay, so now what I want you to do is to go from your test statistic t is equal to negative 10.43, use your t-table, and find the corresponding p-value. Keep in mind that your alternative hypothesis currently says that mu is less than 100. Okay, so go ahead and take a minute to see if you can get the p-value associated with this t, okay? Kind of the steps that you're going to do is you're going to go from a T to a tail, and then from a tail to a P. Okay, so go from a T to a tail area, from a tail area to a P value. Okay. Okay, as I was walking around, it seems some of you guys are struggling with this. Well, let's see what we do. Okay, so what did I say? If your test statistic is negative, what do? We just ignore it, okay? We're going to go to our table. How many degrees of freedom do we have? We have degrees of freedom n minus 1, so we have 19 degrees of freedom. Okay, so we're going to go to our table. We're going to go to 19 degrees of freedom. Okay, and we're going to see, where does 10.43 fit in this lineup? Okay, 10.43 is much bigger than this last number that we have here. The last number we have here is 3.579. We have 10.43, so that goes beyond over here. Okay? Is that okay with everybody? No? We're not okay with seeing that? Okay. So basically, if I told you, so here's 19 degrees of freedom. I'm going to copy this over here. And I'm going to just copy the, why is it, I don't know why my thing's doing this. Copy the column headings over. So I got 10.43, all right? Where would 10.43? 10.43 is bigger than 3.579, so it goes over here. Is that part's okay with everybody, I'm hoping? Okay. My computer. All right, well, I'll just write these down over at the top. Okay, so this was 0.001, or the other column headings, 0.005, et cetera, okay? Things like that, okay? So what we have is that my T is over here, which means my corresponding tail has to be over here, okay? So what happens? Do the numbers get bigger or smaller as we go to the right? The tail areas get smaller, okay? So all we know is that my corresponding tail area is less than 0.001. Is that okay? All right. My alternative has a less than sign. So our directionality matches up because our test statistic is negative, and that's a good thing. But so what is my corresponding p-value? Do I need to double this? No. Okay, so my p-value is also going to be less than 0.001. Okay, so I have t is equal to negative 10.43. I look that up in my table, and I find my tail area. My tail area is my p-value, so my p-value is less than 0.001. Okay, so those are my calculations. And then so lastly, our conclusion will be that, you know, my p-value, whatever it is less than 0.001, okay? So if my alpha is 5%, is my p-value smaller than alpha? Yes, my p-value is smaller than 5%. My p-value is less than alpha, so what do? We reject the null, okay? And we would say we have evidence that, okay, what did our alternative hypothesis state? Yeah, so we have evidence that the average weight of potatoes, or of eggs, yeah, the average weight of eggs is less than 100 grams. Okay, so our friend who claimed that the average weight of an egg is 100 grams, that guy is wrong. We have evidence that the average weight of eggs is less than 100 grams, okay? So now we can settle our argument, and that's that. Yes, question?
So this has nothing to do with the formula x bar plus minus t star?
No, these are hypothesis tests. The x bar plus minus t star times the standard error, that's for confidence intervals, okay? So keep confidence intervals and hypothesis tests separate, okay? Although we're going to do confidence intervals now. All right? So, you know, we have 4 topics to cover today, right? We've done confidence intervals for means with one proportion, or with one sample. Then we did hypothesis test for means with one sample, which is what we just finished up. Now we're going to cover the last 2, all right? But again, everything, it's all the same. It's just kind of the formulas change a little bit. All right, so here we go. So this is new topic. This is confidence intervals. Don't get this mixed up with your hypothesis tests, okay? New topic, confidence intervals. For means with 2 samples. Okay. We have 2 samples, okay? So our data has 2 samples. okay? So what you have to identify, you're going to have to identify 6 pieces of data, okay? You need to have, for sample 1, and for sample 2, you need n, x bar, and s, okay? So to identify that this is the n associated with sample 1, we're going to write n sub 1, x bar 1, and s 1. And to say these are n for sample 2, this is going to have n2, x bar 2, and s2. So these are the 6 pieces of information that you need to know. Sample size, sample mean, sample standard deviation for sample 1, size, mean, standard deviation for sample 2. I don't have to label all of these, right? You guys got this, okay? All right, and now we are making a confidence interval for the quantity mu1 minus mu2. Okay, so we're making a confidence interval for this quantity. What is this quantity? This is the difference between means. Okay, this is a difference between population means. Okay, so for example, if we made a confidence interval for the mean difference between the heights of men and women, our results would be in the vicinity of, I don't know, 5 to 7 inches. Okay, we're asking what's the difference in height between the average male and the average female is basically what we're saying. How much taller is the average male than the average female? Our answer, somewhere between 5 and 7 inches or something like that. Okay, I don't know exactly, but something around there, right? That's basically what we're saying here, okay? We're not saying like the average male is between this and this height and the average female is between this and this height. We're just saying, what's the average difference between your average male and your average female? Okay. All right, so this confidence interval, the formula for that is x bar 1 minus x bar 2 plus or minus a t star times the standard error. Okay. The standard error is just this ugly formula. There's nothing we can do about it. It's s1 squared over n1, s2 squared over n2. Okay, that's that. All right, let me pass around the attendance sheet. So this will be attendance for March 1, 2016. Okay, so please print your name nice and clearly. Pass that around. Okay, so here we go. Confidence interval for the quantity mu1 minus mu2. It's x bar 1 minus x bar 2 plus or minus t star times the standard error. All right. To get your t star, you're going to look it up with the confidence interval or confidence level and the degrees of freedom. Okay, so to get t star, okay, you need the confidence level as before and degrees of freedom. Our degrees of freedom is going to be n minus 1. However, we have two n's. We have an n1 and we have an n2. So which n do we use? Okay, we're going to, between n1 and n2, we're going to use the smaller n. Okay, use the smaller of n1 and n2. So if n2 has 20 and n1 has 15, How many degrees of freedom do you have? 14 degrees of freedom. Okay. Simple enough. And that's that. Okay? What's our margin of error? T star times our standard error. Okay? Critical value times the standard error. Margin of error. Okay, our standard error is this. Critical value is this. This is the center of our interval. Okay. I'm gonna, I guess, do we need to do an example there, or are we feeling okay, right? You just plug in the numbers and you go, and you answers. Okay. Huh? You want to do one? All right. You know what? Okay. Let's cut through it, and then okay. So let's say let's say we make a 95% confidence interval for the difference between the average height of men and average height of women. Okay, so you have sample 1, which will be the men, sample 2 are women, and let's say you get N1, X bar 1, S1, okay, and I'm gonna skip all the work, okay? So we're gonna just pretend like we can plug things into a formula and get an answer, okay? All right, so we're gonna pretend we did the work. Okay? Because I feel like you guys can plug numbers into a formula, right? You just label these things, you plug them into a formula. Let's, for the sake of time, we're gonna just pretend that we did the work, okay? And we're gonna say we get 5.5 plus or minus 1, we'll just say 1.0 inches, okay? So we'll just make it a nice round number. So we've done all the work. We get 5.5 plus or minus 1.0 inches. Okay, so our 95% confidence interval goes from where? What's our low end? 4.5 to 6.5. All right, everybody else okay with that? Right, so the low will be 5.5 minus 1, which gives me 4.5, and on the high end we get 5.5 plus 1.0, which is 6.5. Okay, so this is how we got our confidence interval. Okay, so our statement will be something like, I am 95% confident that the average height of males is between 4.5 and 6.5 inches taller or higher than the average height of females. Okay, so what we're saying is that the average male is somewhere between 4.5 to 6.5 inches taller than the average female. This is basically what we're saying. So if someone asks, do we have evidence that the average height of men and women are different? We would say, do we have evidence that the average height of men and women are different? We would answer Yes? No? Maybe?
Yes.
We would say yes. And why do we say yes? Because our entire interval is positive, right? Our entire interval is positive. Basically meaning 0 is not a plausible value. 0 is not inside our interval. So a height difference of 0 is not a plausible value, okay? 0 is not in the interval. Okay. So a height difference so it's not a plausible value. We would have evidence that there is a difference between the means. Okay. On the other hand, if we did something like, make a 95% confidence interval for the difference between the average IQ of men and women, okay? The average IQ of men and the average IQ of women, and we did a 95% confidence interval for the difference between those numbers, what would we find? Maybe it would go between -5 to +5, okay? And so what that means is the average IQ of men is anywhere from 5 points lower to 5 points higher than the average IQ of women, okay? So would we have evidence that there's a difference between average IQs of men and women? In that case, it would be no, because 0 is inside our interval. 0 is a plausible value for the difference, meaning it's quite possible that men and women have the same average IQs and would have an average difference of 0. Okay? I hope? Okay, well, you have homework this week and, a practice quiz to kind of practice these topics here. Okay, so that's confidence intervals. And then the last thing, all right. Hypothesis tests. So again, new topic, write a bar in your notes. So don't mix up hypothesis tests with confidence intervals. Okay? All right, so our hypotheses. So this is very similar to hypothesis tests for proportions with 2 samples, except instead of P, we've got mu, all right? So what is our null hypothesis? What do you think this is going to be? Mu1 is equal to mu2, okay? Or conversely, or equivalently, mu1 minus mu2 equals 0, okay? Our alternative will then be mu1 not equal to mu2, or mu1 is greater than mu2, or mu1 is less than mu2. Okay, so our preparation, you figure out your alpha, and then you've got to label your data, right? So you got N1, X bar 1, S1, N2, X bar 2, and S2. Okay, so label all of these things. We can check conditions, but all right, calculations, okay? Standard error, S1 squared over N1 over S plus S2 squared over N2. You get a test statistic T, and this is X bar 1 minus X bar 2 divided by our standard error. Okay, so, and then you go from your t, look up in the table, to get a p-value, to get a tail area, and then go from the tail area to get a p-value. Okay? Same rules as before. If you have a one-sided test or one-tail test, your tail area is your p-value. If it's a two-tail test, you double that. You double your tail area to get your p-value. When's the only time we have a two-tail test? When we have a not equal sign in the alternative hypothesis. Okay, so we do this. So this is the only thing that's changed, all right? So the whole process is the same. All we've done, okay, our hypotheses now have mu1 and mu2. We've got all this. It's easy, right? And then our decision making is exactly the same as before. So if our p-value is bigger than alpha, do not reject. P-value less than alpha, reject, right? So conclusions will be same as before. I'll just write that. Okay, so we'll do an example, and this will be our last thing. And I hope we'll be able to do this. Yes, question.
For the degree of freedom, do you do the same thing you do for the other one?
Yeah, okay, oh, degrees, okay, yeah, so when we do this, degrees of freedom is equal to n minus 1, but we have two n's, so which n do we use? Use the smaller n. All right, you guys got this. You guys got this. Okay. Well, you know, and this is where we start answering interesting questions, okay? At least I feel it's interesting. All right, let's try this out here. Whoops. Okay. All right, so problem. Let's see. What is the average weight of a newborn and of an onion? Of a 3-year-old. Okay. We'll ask. All right, what's the average weight of a newborn? 7.5. All right, so we'll say, is the average weight of a newborn we'll say a newborn human different from the average weight of, we'll say, an adult cat. No, what's comparable to? No, dogs are huge. Huh? Is that a good question? Is this everybody? No. Oh. Okay, so we'll say, is the average weight of a newborn human different from the average weight of a cat? Okay, so we took a sample, a random sample of, let's say, 20 newborn babies. All right. Okay, the average weight was, we'll say, 7.5 pounds with a standard deviation of 0.5 pounds. Okay? All right, and then we'll say we took a random sample of, we'll say, 15 cats. I don't know, what's the average weight of a cat? look at that. Okay. And the average weight was, we'll say, 8.5 pounds with a standard deviation of 1.1 pounds. Okay? And so we're going to say, does our data, or do our data, provide evidence that the average weight of a newborn is different from the average weight of a cat? Okay, so we'll start there. All right, I guess we'll do this step by step, okay? So come up with your hypotheses first, okay? This should be easy. I'm hoping. Okay, so come up with your hypotheses. Okay, so for our hypotheses, what do we have? Our null hypothesis is going to be mu1 equal to mu2. Okay, this is always going to be your null hypothesis when you're dealing with means and you've got two samples, okay? Or, I mean, conversely, it might be written this way, mu1 minus mu2 equal to 0, okay? But these two things are saying the exact same thing, right? We can see that. The alternative hypothesis is going to be what? Right, so the key word is in the, is it different here, okay? So we're gonna have mu1 not equal to mu2. Okay, so there we go. So this says the mean weight of newborns and cats are the same, and the alternative says, nope, the mean weight of newborns and the mean weight of cats, those are different numbers, okay? All right. Okay, so just so I have some video proof, I'm gonna call these names out, and these people are not here, okay? So I got Jovanes Supikian, whose name is on here but is not present, and Harud Seropian, whose name is on my list but is not actually here, Victoria Ladian, and then Lani Zakarian, Sasha Zohuri, Arthur Hakobian. Okay, so these names, somebody's signing in, and it kind of indicts those people who are immediately above or below the names on the list, because I'm thinking, you know, when you're signing things in, it makes sense that you're going to put your friends' names either immediately before or immediately after. So these people are going to be on my watch list here, and we'll see if we run into problems next week, okay? Or in the future. Most of you guys are honest, and I trust, you know, you guys are like my superstars because you guys stay, like, I recognize almost all your faces, and no, not extra credit. You guys are getting your attendance points, and these people who are lying on here will not. Yeah, if I didn't call your names, I'm trusting. I'm kind of looking around, and it seems okay here. I mean, I don't feel like going through the entire list here, but anyway, that's always disappointing when you feel like you're trying to be as fair to the students as you possibly can be, and then you still feel like students try to take advantage of you. That's always upsetting. That's life, though, you know? You just gotta, I'm not, you know.
Do we have their attendance points?
Yeah, no, you'll get your attendance points for being here. You know, I don't have a way to prove that someone's lying and signing in people here, but yeah, I think people are smart enough not to to do dumb things like that. Okay, so anyway, let's go on, and we'll go from here. And or actually, let's just do our prep step here. Okay, so our preparation. Let's label all of the pieces we've got. We need to have N1, X bar 1, and S1. And we're going to have N2, X bar 2, and S2. Okay, so let's call sample 1 the newborns. And sample 2 will be the cats. Okay, so go ahead. Let's just shout out these numbers. N1, what is N1? 20. That's how many babies we have. X bar 1, 7.5. S1, 0.5. And N2, 15. X bar 2, 8.5. S2, 1.1. Okay? Everyone's good with it, getting all of these numbers out of the paragraph of text here? Okay, great. Okay, so all we're going to do is now that we've labeled all of our data, we're going to fill in all of our equations, get our values. So standard error, S1 squared over N1, S2 squared over N2. .5 squared over 20, 1.1 squared over 15. Just plugging in S1, S2, N1, and N2. So we're going to have 0.5 squared divided by 20 plus 1.1 squared divided by 15. I hit enter. Oh, it's giving me this nonsense. Okay, and we get this. 0.30523. Okay, our test statistic T is X bar 1 minus X bar 2 divided by 0.30523. Our standard error. So we have 7.5 minus 8.5 divided by 0.30523. So in the numerator, I'm going to have 7.5 minus 8.5 divided by, I'm going to hit the answer button to plug in what we had previously. I get negative 3.276. Okay. All right, let's, I guess I'll give this, give you guys the opportunity to get the, well, we're going to run out of time. Okay, so to get our p-value, we're going to look this up. How many degrees of freedom do we have? 14 degrees of freedom, okay? So degrees of freedom is equal to 14. We're going to look up 3.276. 3.276. Okay, so what do we see? For 14 degrees of freedom, okay, in our table, we have 0.005 and 0.001. 0.005 with 14 degrees of freedom is 2.977, and over here is 3.787, right? Okay, so our value of 3.276 is in between here and here. So our corresponding tail area is in between here and here. So what we have is our tail, whatever it is between 0.005 and 0.001. is my tail area my p-value, or do I have to double this? I have to double it. Why do I know I have to double it? Because my alternative hypothesis has a not equal sign, right? So my alternative has a not equal sign, so I have to double my tail area. So the p-value is between 0.005 times 2 is 0.001, or I mean, sorry, 0.01. And 0.001 times 2 is going to be 0.002. So my p-value is between 0.01 and 0.002. Okay, so all I'm going to do is just going to write that as my p-value. I'm going to write it in this form, is less than 0.01, and 0.002 is less than my p-value, or my p-value is greater than 0.002. Okay, so at this point we're going to make a conclusion. Let's say alpha is 5%. Is my p-value less than alpha or greater than alpha? Yeah, my p-value is less than alpha. So we reject the null hypothesis. What did the null hypothesis state? Yeah, the average weight of babies is the same as the average weight of cats. So we say we have evidence that the average weight of babies is what? Is different from the average weight of cats. Okay, all right, we'll end there. We'll see you guys next week.